Hi, remote honorable students. Sorry you couldn't make it with us today. At the same time we're doing it, but asynchronously you can watch and see what we did today. Oh, yuck. What the heck is this? Don't know. What happened to sand sanitizer? Where did it go? Right there. Okay. Ladies, have you found soap? You did? Good job. Trying to figure out what happened to the sound here. Are you able to find soap? Would you please, in Odyssey, click on, I believe it's a little green ball that will tell you the chemical formula for soap. There we go. Okay, that's working.
It looks like a caterpillar.
It does. It looks like a caterpillar. Some people think it looks like a dragon.
It's like a poisonous caterpillar.
You're poisonous guy. I don't mean to laugh at fears. Fears are always irrational, so you know. Ew. Look at my soap. Ew. Looks creepy. Anybody figure out what the chemical formula is? What? Okay. Does anyone have with them a list of electronegativities anywhere? Yes, you do. Open up the assignment that had to do with polar and nonpolar bonds. Please check electronegativities for me.
The weirdest thing happened on that. Like, it was due tomorrow, yesterday at 11:59. But like, once I submitted it at like 8, it wouldn't let me unsubmit it. So I couldn't do it.
Oh, because I have to look at it before you can submit. You can't. It's
But it was like,
Schoology is weird.
so it said 11:59 and it won't unsubmit.
Oh.
I had to.
So what had happened to those things then? All right. So, ladies. Let me tell you electronegativity values. Hydrogen, 2.1. Carbon, 2.5. Oxygen, 8.5. And at least in this portion of my cell molecule, that's all I need to worry about. What is that over there? Ah, this is an anion, and that is a cation. What happens when cations and anions encounter water? What do they do? Yeah, we can get a current of electricity. We can have an electrolyte solution. We're going to illustrate that in just a moment. Why is water able to separate anions from cations? Water is a dipole. One end could be attracted to the negative charge, one end attracted to the positive charge. Cora's going to tell me which end of water is attracted to a sodium ion. The end would be oxygen. Which end is going to be attracted to the end with the negative charge? So there's a portion of soap that really loves water. Oh, that would make it hydrophilic. And the polar portion of soap is so polar it actually has negative and positive charges. It's called an ion. But soap has another feature to it. How many hydrogens are in soap? 35. How many carbons are in soap? 18. So that's like they have carbon and 2 hydrogens, and then you repeat that like 18 times. And then put one on the end just for that. So Do these hydrogen atoms over here have positive charge? They are attached to carbon. I'm talking about this bond right here. Is it polar? 2.1, 2.5, 0.4. Anybody remember whether or not that's an important number? It is an important number, but you have to be greater than this number to be a polar bond. So what does that mean? Well, that means over here, I got a bunch of stuff that is non-polar. Uh-oh. That means it's hydrophobic. What does that mean? What does hydrophobic mean? Anybody, tell me. You know. If it's philic, it's water loving. If it's phobic, it means you don't like poisonous caterpillars, or you don't like spiders, or you don't like snakes. You can have a phobia about deadly snakes and caterpillars, and it's fine. You're hydrophobic if you're nonpolar. You're hydrophobic if you're nonpolar. By the way, I'm bicycle-philic, not bicycle-phobic. Is anybody going to join me on, what is it, Health Day? Wellness Day? I know, don't do that. But is anybody going to join me on my little bike tour on our Wellness Day? What day is that, by the way?
Next Thursday.
Next Thursday?
I'm so excited.
You're so excited.
It gives me off the day where I have so many classes I don't know.
So we're about to learn why hand sanitizer and soaps work so effectively against coronavirus.
Wait, is it this room there? Oh, there.
Aha, look, I have some soap. Do you see soap? I have water. Do you see water?
Yeah.
What do I have here? Okay, what's going to happen?
It's gonna, their densities are different.
Is oil hydrophilic or hydrophobic?
Hydrophobic,
Are you sure?
because they don't mix.
Yay. Yes, this is definitely going to end up a greasy mess. Can you tell where the oil ends and the water begins?
Yeah.
Pretty easily. If anybody has an iPhone with the 3 cameras on the side, 3 lenses, I need your help. I want you to do a little video for me. So that's the one. I would like to show you something interesting that happens between oil and water. Heck yeah, come on up, take a video for me. And this is for our friends at home. So I'm gonna go here and stop that share. Oh yay, we're right there. Heck yeah. Lovely.
Just film this, right?
Right. Ladies, would you stand just ever so slightly off? There we go. Perfect. Right there, right there, right there. Okay. Ladies, what do I have in my hand now? Tell them.
Oh, green, food color.
What do I have in my hand? What color?
Green.
What color? Thank you. Watch carefully. Are you watching? Are you watching? Are you watching? Okay. Uh-oh. Oh. Oops. Oh, yeah. close now. Thank you so much. Yeah, heck yeah. Oh my goodness. My food coloring is actually mostly water with a few molecules of a dye in there. But what happened? That's a great shot, by the way. So tell them.
Oh, it's sitting at the bottom of the oil.
What shape are they making, Tyra?
Sphere.
Spheres. Anybody in math? Oh yeah. Have you ever heard of a minimum surface?
No.
Okay. If I have an object and I put it in a sphere, I've minimized the outer surface, because if I put it in a cube, those surfaces are much larger. So for a given volume, a sphere has the least surface area, a cube has the most surface area. Yo. Absolutely, surface area to volume. So I've taken all my molecules, I've joined them as close together as I can. I prevented them from interacting with the outer side as much as possible. I can't prevent it completely, but I can avoid it by making it a sphere. And you see that. Oh, a little something called surface tension is being illustrated here. What makes water stick to itself is something we're going to explore today. Whoa. What do I have in my end?
Salt.
Why is it kosher? Because it's pure. There's nothing else but soap. The sodium, salt. What is salt? Let's put some sodium chloride solid into our little mixture of things. Uh-oh, it doesn't want to interact with the oil. Oh no, there it goes to the bottom. Oh, wait a minute. What's going on? Holy cow. The salt has dragged oil down to the bottom. And now the oil floats back up. Oh, wait a minute, what happened there? We lost surface tension. Oh my goodness. Let's try that again. Where has my dye gone? Why didn't it do that in the first place? Because as it interacted with the oil formed a coating around it, which was spherical, to prevent, as much as possible, the interaction between the oil and the water. Now they had to interact as I put them together, but they created spheres. Those spheres then went to the oh, look, there's another one of those little spheres. Oh no, now the salt has dragged it down. Which is the most dense of the materials that I put in here? Is it the oil, the dye, the water, or the salt? Salt is the most dense. You can still see, although it's dark because of the food coloring, every so often, little spheres of oil are rising from the bottom to remix with the oil that's there. Density and polarity are the things that are coming into play here. Let's do this one more time. Are you ready? There. Okay. At first, whoa, the salt actually has a lot of air associated with it. So we gotta get rid of the air. That's why it doesn't sink right away. The oil then coats the salt. Oh, now the salt is more dense than anything else, sinks to the bottom. Anybody ever heard of a lava lamp? What's a lava lamp? Where is the lamp part of a lava lamp? It's down here. Why? Because when you heat certain oils, they expand, become less dense, and then they rise. But then when they rise to the top, they cool off, they become more dense again, and they sink back down. That's how a lava lamp works. But here I don't have heat. I don't need it because oil and water avoid each other in such a way that I can manipulate it using salt. The salt gets coated with the oil because it doesn't want to interact with the oil. I made it interact with the oil. So the oil coats it in a sphere to minimize the interaction between those two substances. That sphere gets dragged down because salt is so dense. It hits the bottom, the salt gets dislodged from the oil rises, the salt stays. One more time. Watch carefully, here we go. Okay. When it spreads out like that, there's too much surface area, it doesn't really want to interact at all. But then the oil starts to displace the air that's around each of those crystals. Boom. Oh, that was a good one. Did you like that one? Did you get that one?
Yeah.
Tyra, thank you so much. Oh, wait, not done. What happens if I mix these two? Let's see. Okay, this is going to get messy. I usually have smaller containers to do this. Oh, no. What's happening up here? Now, because the surface of my glass is a little bit scratched, I was trying to clean it really well, but I ended up scratching it. The oil actually adheres to some of the little scratches. It's not going to be perfect in the way that it re-separates, but it's going to come pretty close. Uh-oh, what happened to the salt?
Oh, gathered at the bottom.
Down at the bottom. Has it all dissolved? But it will. Give me a sec. All I'm going to do is put a top over this so I can mix it a little more easily. Not make such a big mess. In your notes, ladies. I'd like to see a sodium ion and a chloride ion. Then I would like on the right side of the page, what does one chloride ion look like surrounded by water? What does one sodium ion look like surrounded by water? In your final picture, you need at least 4 water molecules.
Okay, so are we done recording?
You're done recording. Oh, wait, no, I have one more thing to show you.
Okay.
Now, where did the salt go?
Oh,
It's not at the bottom anymore. Oh no, there's no crystals left. Magic. No, what happened to the salt? Yeah. Did you show me how to dissolve? Here's what I'm looking for. Here's a sodium ion. Oh yeah, I have it over here. Here's a sodium ion. Tyra, tell them what I just wrote on the board.
The plus.
A plus sign. Here's my chloride ion. Why is it bigger? Because it is an anion. It's always bigger. Then I add water. That water is going to go underneath here. We'll explain in a few days why that's there. My water better look like this around sodium. For those at home, I'm putting the oxygen close to my sodium ion. My chloride ion better look like this. My H's are closer than my O's are to my chloride ion. Dissolving is a big deal. Sorry that I jammed it up over in the corner, but I was hoping people have folks to this real quick. Yo, what's up? Heck yeah. Here's sodium and there's chloride. Then I got water. Now I have sodium ions and chloride ions surrounded by water. Take a message here. Can you draw water in the vicinity of any ion? Yes, you can. Now you can. Yo, what's up? Say again? Draw this part? Okay. Why have I put oxygen close to sodium? Because what? Attraction. Why are the hydrogens away from the sodium? Okay. Why are the hydrogens attracted to chloride? Why is the oxygen as far away from chloride as it can get? There you go.
So why did you draw? Aren't the two separate? Because
Here's my salt to begin with. Okay. Here is my salt afterwards. Do you see any solid salt in here?
I'm just asking, like, is the top portion separate?
Sodium. And then the chloride is separated by water from the chloride. I jammed it into a little corner just to make life simple.
So we are gonna have to go through some.
One of those two. Now, ions are attracted to water. Whether they're cations or they're anions, there is a net attraction. Nice. Okay. What do I hold in my hand, people? I need some video again. Where's this soap gonna go? Predictions. Please predict for me. Where's the soap gonna go when I pour it in? Somewhere. Into the thing, of course. Yeah. Is it gonna go on top of the oil, top of the water, all the way down to the bottom? Where do you think?
I don't know.
I don't either.
Okay, wait, it's hydrofiller.
Well, let's see.
Wait, no. It has,
It's what?
Yeah.
I need a lot, so I'm just gonna take several. Oh, wait a second. Where's it going? Oh, right in between. That's weird. Oh, now it's saying, oh, no, most of it's floating right in between. Yes, some of it's saying. Okay. Soap eliminates surface tension. Soap eliminates surface tension. And let's prove that. It's surface tension that's keeping the oil and the water away from each other because they have different forces of attraction. But the soap likes them both. Whoa. Yikes. That's a mess. Wait a minute. Where'd the oil go? Where'd the water go? I don't get it. Well, let's watch hand soap versus hand sanitizer versus the coronavirus for an explanation of what's going on here. Let's do that. Yay, woohoo. Are you ready? You ready? I'm ready. I'm so ready. What are you over? Coronavirus? Old news. Here we go, people. Do you have a picture of soap nearby? Are you able to hear it? Whoa, what happened there? Okay, hold on. There we go. Okay, fine. Hopefully this won't kill anybody. Hands are.
Face.
There we
A
go.
virus can infect you, but there are two extraordinarily simple ways you can keep that from happening: soap and water and hand sanitizer. So, which is better? The coronavirus that causes COVID-19 is one of many viruses whose protective outer surface is made of a lipid bilayer. These lipids are pin-shaped molecules whose heads are attracted to water. And
Okay, so in Odyssey, what you have is a phosphate group. Ladies, tell me what a phosphate ion has for its formula. PO43-. We make a connection between that and a chunk of carbon called glycerol. You don't need to write this down. But attached to those glycerol molecules are long molecules that look a lot like soap, but we call them fats. Actually, we call them fatty acids. This is a lipid. At one end, I have a charge. At the other end, I have a bunch of carbon-hydrogen bonds. Are carbon-hydrogen bonds polar or non-polar? Non-polar. I've got an end that loves water, hydrophilic. I've got an end here that avoids water because it's non-polar. It doesn't want to mix with water.
And tails are repulsed by it. So, in water-rich environments, lipids naturally form a shell like this, with the heads outside and the tails inside. Their shared reaction to water makes the lipids stick loosely together. This is called the hydrophobic effect.
The what effect? The what effect? So what it's saying over here is that water forms an interaction called a hydrogen bond. We'll explore what a hydrogen bond is very shortly here. Those hydrogen bonds involve polar molecules, but a lipid has a big chunk that's nonpolar. It has to avoid water. It's hydrophobic. It's the attraction of water molecules towards each other that gets interrupted by nonpolar molecules that water doesn't like. So water says, hey, we're sticking together. We're forcing out those molecules that are nonpolar, creating the hydrophobic effect, creating a lipid bilayer. Every cell in your body has one of these. And so does the coronavirus. A lipid bilayer.
Outer structure helps the molecular machinery of the virus break through cellular membranes and hijack our cells. But it has thousands upon thousands of weak points where the right molecules could pry it apart. And this is where soap comes in. A single drop of any brand of soap contains quadrillions of molecules called amphiphiles, which resemble biological lipids. Their tails, which are similarly...
So the tail of soap is just like the tail of our lipid. So they match up. They have similar interactions. They're nonpolar. The head of soap is like the head of a lipid, and it wants to be sticking out into water. Amphi means both. Phile, loving. What are the two things that soap loves? Oil and water. Non-polar and polar substances. It likes them both.
Similarly repulsed by water, compete for space with the lipids that make up the virus's shell. But they're just different enough to break up the regularity of the virus's membrane, making the whole thing come crashing down. Those amphiphiles then form bubbles of their own around particles, including the virus's RNA.
Now, Odyssey has a picture of what happens when you reach something called the critical concentration of soap. What happens? Ugh, this is getting really slippery and dangerous. Well, I have a lot of oil in here, but I need several molecules of soap for every molecule of oil to form into what's called a micelle. Now, you see bubbles up here. I agree, those are bubbles, but that's what soap does sometimes. But down here, do you see a separation of oil and water? Nope, because every molecule of oil is now surrounded by soap. And the soap has an end that likes to be surrounded by water. So I've broken up my oil, eliminated this thing called surface tension, and now I have what we call an emulsion. Emulsions and colloids are things that we'll talk about in the near future. You don't have to write that down, but you do need to know that soap is an amphiphile. It loves to be surrounded by water. It loves to be surrounded by oil. And we use that property then to wash away dirt. In this case, I'm illustrating that the oil, which normally would be aggregating up at the top here, nope, it's now surrounded by individual molecules of soap. And the soap is causing those lumps of oil now to be surrounded by water. I can wash this down the drain. I've cleaned my glassware. It has a polar end and a non-polar end. A polar end and a non-polar end. Hydrophilic at the top, where we've got polar bonds or charges, phosphate. And then at the tail, we've got nothing but carbon and hydrogen, which is non-polar. Yo.
Or lipids.
Lipids are hydrophobic. We have a lipid bilayer that results because one end of our phospholipid has a charge. So a phospholipid is a subset of lipids. The lipids are fat soluble.
Do we need to understand this for the next?
Well, you need to understand that there's a difference between polar and non-polar substances.
Yeah, but like just like how it fits into RNA.
Heck no. Okay. But let's keep going.
Apply water and you'll wash that whole bubble away. Hand sanitizers work less like a crowbar and more like an earthquake. When you surround a coronavirus with water, the hydrophobic effect gives the bonds within the membrane their strength. That same effect also holds the big proteins that form coronavirus's spikes in place and in the shape that enables them to infect your cells. If you dry the virus out in air, it keeps its stability, but now surround it with a high concentration of an alcohol, like the ethanol or isopropanol found in most hand sanitizers. This makes the
Do we remember or know or have discussed, I think we discussed it very briefly, an alcohol, carbon, oxygen, hydrogen. This is called ethanol. Propanol would have one more carbon sticking off the top here. Ethanol, or rubbing alcohol, isopropyl alcohol, are effective at destroying the hydrophobic effect because they're actually more non-polar than they are polar. They're more non-polar than they are polar. And yet they've got both going on. So it really messes with water's attraction to itself.
hydrophobic effect disappear and gives the molecules room to move around. The overall effect is like removing all of the nails and mortar from a house and then hitting it with an earthquake. The cell's membrane collapses and those spike proteins crumble. In either method, the actual process of destroying the virus happens in just a second or two, but doctors recommend at least 20 seconds of hand washing because of the intricate landscape that is your hand. Soap and sanitizer need to get everywhere, including your palms, fingertips, the outsides of your hands, and between your fingers to protect you properly. And when it comes to a coronavirus outbreak, doctors recommend washing your hands with soap and water whenever possible. Even though both approaches are similarly effective at killing the virus, soap and water has two benefits. First, it washes away any dirt which could otherwise hide virus particles. But more importantly, it's simply easier to fully cover your hands with soap and water for 20 seconds. Of course, hand sanitizer is more convenient to use on the go. In the absence of a sink, use the sanitizer as thoroughly as possible and rub your hands together until they're dry. Unfortunately, there are billions of people who don't have access to clean drinking water, which is a huge problem at any time, but especially during an outbreak. Researchers and aid groups are working to provide solutions for these communities. One example is a device that uses salt, water, and a car battery to make chlorinated water that kills harmful pathogens and is safe for hand washing.
You don't have to worry about this part.
So wherever possible, soap and water are recommended for a coronavirus. But does that mean it's best for every viral outbreak? Not necessarily. Many common colds are caused by rhinoviruses that have a geometric protein structure called a capsid instead of a lipid membrane.
Did anybody catch a cold over the last 2 years? Yeah. Was it COVID? No, because they're two different viruses. And it turns out that the one that causes the respiratory infection that we call a cold is simply a tougher version of a virus. and that the coronavirus is actually more susceptible to soap and water.
The capsid doesn't have nearly as many weak points where soap amphiphiles can pry it apart, so it takes longer for soap to be effective. However, some of its surface proteins are still vulnerable to the destabilizing effect of hand sanitizer. In this and similar cases, hand sanitizer may be more effective, especially if you then wash your hands to remove residual particles. The best way to know which to use for any given outbreak is to do what's best for all things illness related. Follow the advice of accredited medical professionals. Need help timing 20 seconds of hand washing? Start now. Wow, nice clean hands you have. Oops, don't touch your face. You look well rested. Have you been stretching? Must be all that water you're drinking. Happy birthday to... I don't think we have the copyright on that. Well, happy birthday. I forget the words. Has it been 20 seconds yet?
Okay, in Odyssey, I'm going to come around and have you do the, going to have you share your screen. In Odyssey, I would like you to build a molecule. The molecule has to have one polar bond at least, but it has to be a non-polar molecule with at least one polar bond. I'm going to put, hold on just a second. Let me see where. New share. Am I still recording? I'm still recording. Yes, indeed, I'm still recording. Share, and that share. There we go. Okay. Now, how to do this? I'm going to stop my AirPlay. Okay. The number's going to come up in just a moment. I'm going to ask you to share your screen with me with Odyssey going. Where to go? Where to go? Come on, AirPlay. All right. I'm going to ask you to share your screen with me as soon as we get this number going. Oh, would you please on your computer, and it has to be one at a time, Cora, just because you're going to be first, Cora, not just this instant. Can you build a molecule with a polar bond, but the molecule itself is non-polar? Let's look at an example. And what I neglected to do, which I intended to do. Where's my electronic activity? Oh, wait, I don't know. So Cora, are you ready for me? Sorry, I didn't put those up sooner. Yo, what's up? So in a moment, I'm going to ask Cora to do this, but all of you need to look carefully. Up at the top corner of my screen, there's this little image of my computer screen, and I'm going to turn off my AirPlay, and you have to turn your AirPlay back on. So it's looking for it up at the top, or you go to your system preferences, you choose AirPlay, and you can project your screen. Cora, are we feeling comfortable about sharing our screen with a model? Go for it. We'll help you out then. I'm sorry?
Oh, wait.
You're trying to go to the chemistry lab. Mhm. And when you do that, a number is going to pop up here. Then you type that number in, and there you go. That's the code you need. Ladies, what element makes the greatest number of bonds that we've talked about? What element makes the greatest number of bonds that we've discussed? Carbon. Let's start with carbon. I would like Cora to choose an element that's going to make a polar bond to carbon. Can we help her out? Oxygen. That's pretty electronegative. Go ahead. Let's add an oxygen. Add another oxygen. Do we have polar bonds in this molecule? Yep. Is this a stable molecule the way she's drawn it?
No.
Oh, bummer. Cora, can you see the little button that I'm pointing to?
Yeah.
Click that. Click on any of the free valences from one. Oh, there you go. And now, nope, not that one. To oxygen now. A free valence on oxygen. Yay. Do the same. Yay. Does that look like carbon dioxide to you? Would you now press on this little key that you see down here? Yep. Yay. Can you do the stretching motion so we can see a bigger picture? Yay. Can you double click on this little red arrow? I don't know why it's there. If you keep clicking, eventually it'll go away. Build a molecule. Overall nonpolar, but it contains a polar bond. Yeah. Yay. Now, yay. Okay. Would you please share your screen? Would you please stop your AirPlay, and then we'll go to AirPlay over there. Okay, so let's take a look at what's happening here. Here, I have soap bubbles. No surprise. Soap has a portion that likes to stick in nonpolar air because air is nonpolar, which are nonpolar molecules. But then it makes a very thin film where there's a little bit of water, and then there's another layer of soap with the ends of soap sticking out. In other words, this is an inverse bilayer. Same properties are going on, but it's exactly inverted to what you've seen. The water is in between two layers of lipids with their hydrophobic ends sticking out this time into air. That's what makes a bubble. I have what we call an emulsion right here. Emulsion? Molecules of oil that are surrounded by soap and dissolved in water. That emulsion continues here, but you see it kind of fading a little bit. I don't have enough soap to surround every molecule of oil. It would take this whole bottle because I had about this much oil in there. And then down here, we see that it's starting to separate a little bit. That's the water that doesn't have any of these soap oil combinations in it. Eventually it separates, but I mix it again and it will completely emulsify. Oh, that's the basis for making mayonnaise. Yo. We decided to make carbon with oxygen because that's a convenient polar bond. Two polar bonds. Why was that a nonpolar molecule? Share with us again. Because the two polar bonds are exactly opposed to each other, and we call that symmetric. Symmetric molecules are non-polar.
And so the reason H2O is polar because it's not symmetric.
And the symmetry is thrown off by the lone pairs that exist there.
Have a lone pair, it makes it unsymmetric, which makes it polar.
Bingo. Okay. And so let me, go and unsubmit all of these assignments because I do want you to have a look at those.
Dioxide, the reason why it's non-polar, I mean, is because it's linear. So symmetry beats all. It's polar, but it's symmetric, it's non-polar. Yeah. So symmetry beats all. That should be a good thing.
Oops.
So, but it has a low state that automatically. Yeah.
Be careful.
Well, like if it's already polar.
Okay. So take a look at what I have on screen. I'm going to unsubmit your work so you can see this as well. What's going on?
Correct.
I don't understand.
So if it's polar, like if it's greater than 0.5,
Give me a new one.
then it's unsymmetric, then it's polar.
There we go.
But if it's
I don't want you to see that.
greater than 0.5 and symmetric, it's not. I got you now. Oh my god.
Where is it? Come on. Oh. Dang it. Okay. So, ladies, I've got a little activity for you to do right now. And I have a quizzes. I got all kinds of fun stuff. We should definitely do that.
Food makes chemistry so much better. Like,
Quizzes do.
food and quizzes are my favorite thing in the world.
Okay,
They
where?
just make me so happy that
Wait, what is going on here? Oh my God, I hate Schoology now.
I try to do that.
Okay, so what I'm doing here is I'm just unsubmitting everybody's work. Don't worry about deadlines.
Yeah, I submitted after
Got it.
deadline, so I actually finished it. I just wanted to check my work. just
Got
in
it.
case. So it was an accident. That's how I was
Okay.
11:59.
So what I want you to do is open this assignment so we can take a look at what we've got so that you're able to see this portion. Because it looks fine on screen, but we need to see it as big as we can. Now, this is a difficult diagram to sort out. And I've got a little assignment for us to work on sorting this out. But do you see that a molecule contains two independent features? A molecule is a collection of bonds. Yes, that's true. But it is also a shape. And bonds and shapes, they're independent. Now, are there any symmetric molecules that are polar?
No.
Why not?
Symmetry beats all.
Not quite. It doesn't beat everything. But what it does do is it says, look, if you have polar bonds, but they're symmetrically arranged, they're going to cancel each other out. If I have nonpolar bonds that are symmetrically arranged, I don't have anything to worry about. There's no charges. I can't be polar if I don't have a polar bond. Okay. Now let's look at a column then. What defines a nonpolar bond? Yeah, a small difference in electronegativity. Are there any polar molecules lacking polar bonds? Are there any polar molecules made up of nonpolar bonds? Look carefully at the diagram. What do you see in the column where the bonds are nonpolar? I see two boxes. The first box says nonpolar molecule. The second box says, oh, nonpolar molecule. What do I need to be a polar molecule? I need two things. What are the two things? Yeah. I need a polar bond and I need something that's uneven in its shape. that make sense? All right, I have a little activity for you to do. The quizzes is coming up. I had this all set up for you. Obviously, I didn't. So no. Where to go? Where to go? Come on, come on. Oh yeah. Go, 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 go. Oh yay! I'm gonna have you do both of these. I had this done already. Okay, so would you please go into Schoology? You're gonna take me a second here. Got it. Move, 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 move. Oh man. Would you now please make any polar molecule in Odyssey? And I'll get back to you. Where'd it go? There's yeah. Come on. Come on, hurry up. Make a polar molecule, any polar molecule you like.
Bam.
Yay. Uh-oh. You kind of like it? Oh, yeah. It takes a while, huh? Silicon trichloride. Okay, now, but wait a minute, a second. Silicon trichloride doesn't exist. Ah, that would be a nonpolar molecule. There you go. There, it doesn't exist. That's why I was confused. Come on, where are you, Schoology? Ah, come on. Oh my goodness.